Hey guys, Mr. Newman here, and today we're going to learn about sequences and series. So first of all, a sequence is just a list of numbers. For example, 1, 3, 5, 7 is a sequence. It doesn't need to be in order like that. It's actually just any list of numbers, but certain lists of numbers there is an order to that we can figure out and calculate and use. So first let me show you about subscript notation. The sequence above, a sub 1 is equal to 1, and we say it a sub 1 like that. Not A1 or A2, but it's A sub 1, and that means the first term of the sequence. A sub 2 means the second term, and the second term is 3. A sub 3 means the third term. A sub 4 means the fourth term. So A sub n means the nth term. In other words, a term that maybe we don't know yet or we want to generalize so we can make a rule. So let's do this. Down here I've given you a formula. I want you to write the first 4 terms of the sequence given by the equation. Well, a sub n is equal to 3n minus 2. The first term is when n is 1, so I'm going to plug in 1. When a sub 1, when n is 1, I'm going to plug the 1 in, kind of like function notation, and we get 3 times 1 minus 2, which is 1. So a sub 1 equals 1. A sub 2, you plug in 2. The second term is 4 when you do the math. A sub 3 is 7, and a sub 4, when you do the math, is 10. So the first 4 terms of the sequence are 1, 4, 7, and 10. Let's try this next equation here. A sub 1 is when you plug in 1 there. That's a negative 1 to the first power is just negative 1, so you get 2. If you plug in 2, negative 2 squared is positive 1, so 3 plus 1 is 4. A sub 3 is 2 again, if you do the math, and a sub 4 is 4. So our first 4 terms of our sequence are 2, 4, 2, and 4. This negative 1 to the n power is a nifty way to, we call it oscillating or periodic functions to repeat between either positives and negatives. So for example, in this one, if I plug in 1 here, I get negative 1 over 2 times 1 plus 1. That's negative 1/3. But if it's an even number, that negative 1 to an even power is going to become a positive number, and so we get positive 1/5. A sub 3 is negative 1/7, and a sub 4 is positive 1/9. So the first 4 terms of my sequence are negative 1/3, positive 1/5, negative 1/7, and positive 1/9. And notice I achieved that by putting negative 1 to the n power. That will be helpful when we go and try to figure out these explicit formulas from a sequence. So, just a real quick note on explicit versus recursive equations. What I had given you before, a sub n equals 3n minus 2, that's an explicit equation. And in other words, if you want to find the 100th term, you just plug in 100 and you get it out exactly. A recursive equation works a little differently. You notice here that each of these goes up by 3. So one way to write this, yeah, that's the explicit one. One way to write a recursive equation is to say a sub n, that's the current term, equals a sub n minus 1, that's the previous term. And if you want to check that out, you just plug in a number like 5. N minus 1 is 4, so if we're looking for a sub 5, we're going to use a sub 4 there. And then plus 3. So the formula is a sub n equals a sub n minus 1 plus 3. In other words, take the previous term, add 3 to it, and get the current term, or the next term. And whenever you have a recursive equation, you need to define the first term, otherwise you don't know where we're starting. And in this case, a sub 1 is 1. So that means the first term is 1. Do this. I want you to try and write the explicit and recursive equations for this next one, and I'll show you how to do it in just a moment. All right. I'll do the recursive first. A sub 1 equals 1. I probably should have switched that up, but we again started at 1. A sub n is equal to a sub n minus 1 plus 2. In other words, the current term is equal to the previous term plus 2 each time, because it's plus 2 to get to the next one. An explicit equation, a sub n is equal to n to n minus 1. And if you're wondering, how did I get that minus 1? Well, one of the things is that this equation looks like, or it is a linear equation, so it looks like y equals mx plus b. Well, b is my y-intercept. And if you remember, the y-intercept is when x is 0. What's weird is we're using n here, and n typically starts at 1. So if we want to find a sub 0, when n is 0, we need to go back one. And you notice if we walk backwards in the pattern, the next term before this, 5, 3, 1, the next term before that is going to be -1. So a sub 0 is technically -1, just like a sub 1 is 1, a sub 2 is 3, and a sub 3 is 5. So that's where I got that from. Go ahead and try to write the explicit equation for that last one there. All right, did you get it? Here's what I got. A sub n equals 1 over n squared. And notice we can't really get a good recursive equation, or not an easy one anyway. It is possible if you want to do it, knock yourself out, but it is a bit trickier, and so I want to ask you to do that. All right, next, summation notation. This always scares students when they first see it, but once it's explained, it makes a lot of sense. First of all, this is a way of adding up a sequence. We call that a series, if you're adding up a sequence. So this right here, this notation, the I equals 1, that means start at 1. We're going to start our sequence or a series at 1. The variable is always given right there on I equals, and that can change. As you notice below, we have a different variable. That's fine. We want to know what is our variable in this situation. Notice inside the function, that's 3i right there. I think of that as inside because they're kind of like parentheses there for me. That I is the variable that we will be replacing. And the 5 on top just tells us when to end. So let me show you how we write this out. 3i. What I'm going to do is I'm going to write out 3i, but instead of I, by the way, it's a summation notation, 3 times blank. And I'm going to replace it with what I is equal to, 3 times 1. Then I'm going to write plus. This plus is because we're summing these. So every term of the sequence, we're going to put a plus between. Then 3 times I again, but now I is going to go up by 1 to 2. And then we're going to add 3 times, the next one is 3. Notice we're just changing out I, and the i's start at 1 and go all the way up to 5. That's our end value. And before I get too much further on this, notice that I'm just putting a plus between each of these, and I'm just rewriting 3i over and over, except I'm replacing I with 1, 2, 3, 4, and 5. That 3 times 1, 3 times 2, 3 times 3, 3 times 4, and 3 times 5 becomes this right here. And when you add all those up, I believe you get 45. That is how you use summation notation to calculate a series. Let's try the next one here. Notice we have a different variable. That's just fine. Fortunately for us, k is also inside of the function there, inside the parentheses. So I'm going to write the function out, 1 plus blank squared, and instead of k, I'm going to put where we start. Well, we start at 3, so this time I'm going to put a 3 there. We are always increasing by 1, so plus the same thing over again, but I'm going to increase that 1 up to a 4th. And then do it again and again and again, all the way up to 6, because that is the end. That is how you sum 1 plus k squared from 3 to 6. So when you add all these up, you get 10 plus 17 plus 26 plus 37. And I believe when you add all that, you should get 90. All right, last thing I want to share with you is the factorials. Factorial is an exclamation point in math. And when you put it behind a number, it means to multiply all the way down to 1. Sequentially. So, for example, 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, 4 factorial is 4 times 3 times 2 times 1. So 5 factorial, you guessed it, is 5 times 4 times 3 times 2 times 1. Now, those are actual numbers, right? So like 2 times 1 is 2, 3 times 2 times 1 is 6, 4 factorial is 24, and 5 factorial is 120. That's really useful when you talk about permutations and combinations later on in statistics, but I wanted to show you guys the factorial. All right, thank you for watching.